Hey, pre-calculus friends, we're here in chapter 3, looking at section 3.5. We are going to be talking about continuity and end behavior. So here's our vocabulary. It's not as extensive, but we should get in there anyway. So a lot of the words here are going to deal with the idea of continuity, literally all except two. So continuity, and before we even get started, is being able to draw a graph on the XY on an XY table without lifting your pen. All right. So this would be considered a continuous graph. I just drew a continuous graph. This red one is considered a continuous graph because, theoretically, if I had all the time in the world and I had all the paper in the world, I could draw this graph without lifting my pen, without lifting my marker. All of these graphs that I'm drawing are considered continuous. Make sense? Even if I had something that was asymptotic to the x-axis where it got closer and closer but never crossed, all of this is considered continuous. So we kind of got through here, but let's go back and figure out what discontinuous is, or what are some of the types of discontinuities we can have. So discontinuous means you can't do that. Discontinuous means that there's a break and a point in the graph or a space in the graph where the graph does not exist, even if that space is like just one point. There is, or one location. So I'm going to zoom in a little bit on this picture here so you can look at some of these types of discontinuities. This discontinuity, if we were to graph 1 over x squared, we would see it's got this kind of volcanic vibe where each side is asymptotic to the y-axis. And what you're going to realize here is that all of the values all the way up to 0, and if you think about plugging 0 in here, you know that we'd be dividing by 0. That would be a problem. So all of the values approaching 0 of the function as x approaches 0 are going to be super high. They're going to go to some infinity. Sometimes you can have infinite discontinuities that do it in the opposite way. So this would be an infinite discontinuity if this part of the graph didn't exist and it was more like this. Infinite discontinuities means that you've got part of your graph going off to infinity as it approaches a number, in positive infinity or negative infinity, and that is considered an infinite discontinuity. All right. Over here, we have a jump discontinuity. The graph seems to be doing its thing really nicely, and then boom, it jumps somewhere else, and it starts to handle itself. And you can see that very nicely expressed in this piecewise function. Over here, we have what is called a point discontinuity. And I like to literally think of point discontinuities as this. If I can walk up to that graph and put my finger on it, let's say that's my finger, and then make the whole thing continuous, then that is a point discontinuity. If I could literally just, in a sense, fill a point, and that would make the whole thing continuous, it would be all good. Notice the difference between a jump discontinuity and a point discontinuity, all right? Okay, so with that, you have been briefed on 3 major types of discontinuities. And these guys you're going to see again in calculus. So that's why it's a good idea to familiarize ourselves with this now. All right, so the next one is an everywhere discontinuity, which literally can't be drawn. So everywhere discontinuities would be a discontinuity that would be expressed as let me see if I can do one. So let's say I had a function f of x such that the function is equal to 3 if x is a real number, if x is rational. So you know what rational numbers are, numbers that can be written as a fraction, and then 4 if x is irrational. So numbers that cannot be written as a fraction. And if you think about this, if we're thinking about the number line, what you're going to realize is that these numbers are peppered all over the number line. Here and there, we've got rational and irrational numbers side by side. But what is side by side? Because no point is side by side, right? So you think right here is pi, and that's irrational. What comes after pi? Is it another irrational number? Let's say the number that comes after pi is 3.2, but certainly there's numbers in between. So as we start to just break down the number line and think about where does a rational number and an irrational number sit, you realize that this is going to be crazy. And so if we were to attempt to graph it, which I shouldn't be doing this anyway, this would be 3 and this would be, this is 3 and this is 4. We'd have, okay, that's not helpful. But you guys get why this is not continuous, it's discontinuous everywhere, because there's no like two numbers that are next to each other that are necessarily rational or irrational. Take some time to ponder that. That was a wild one. All right. So we've got through those definitions. We've done infinite discontinuity, jump, point, everywhere discontinuity. Hopefully I did that kind of okay. On continuous functions. And so we talked about continuous functions are going to be functions that don't have any of these problems, are going to be like the ones that I drew earlier. Now we're going to talk about end behavior. So end behavior is really a concept that, again, you're going to talk about in calculus. What you're thinking about is, where is this function going that I've drawn? Where is this function going? What's happening as I go off to positive infinity and negative infinity? So really, end behavior is asking the question, as x goes to infinity, what's happening to f of x? And as x goes to negative infinity, again, what's going on with f of x? So if I were to draw a picture of, let's say, something that you're familiar with, let me draw the picture of a quadratic equation, and let's make it an unhappy parabola, like so. We could answer this question by looking at it, right? We could say, okay, well, as x gets bigger and bigger and bigger, f of x is getting smaller and smaller, but like negatively infinitely smaller. So the answer to this problem would be negative infinity as x approaches infinity, y or f of x is approaching negative infinity, and as x approaches negative infinity, so now I'm thinking about these values back here, f of x also approaches negative infinity. So that's the end behavior. I'm thinking, our graphs do all kinds of funky stuff, and right? But end behavior is not concerned with all of this stuff here. End behavior is really concerned with what's happening as x approaches infinity, positive or negative infinity. And then so we have this concept of monotonicity. It's not a word that I use every day, I'll be honest. So monotonicity is this idea of the function having an interval where it just increases or it just decreases. Also, again, a very poignant topic that you will discuss in calculus. So let's make sure it makes sense. It's not a hard concept at all. It really is just vocabulary around something that you've probably already thought about. So I can look at this function here that I'm going to graph in green and say, oh, this function has monotonicity over the entire real numbers, over all reals, right? Because as we go from left to right, there is a consistent increasing that's happening. Every value is higher than the one before it, so it has a certain level of monotonicity. I would assume that we could also use that word to talk about something like this, where we can talk about monotonicity not over the all reals for this parabola, but let's say this is -1 and that's where the vertex is. We can talk about monotonicity from -1 to infinity. So this function has monotonicity over a particular interval. And it doesn't have to all be just going positive. It could be monotonicity also from negative infinity. We wouldn't use that bracket there. We'd use a parenthesis. Monotonicity from negative infinity to -1. Does that kind of make sense? I'm hoping it does. Let's get started looking at some other things in just a moment. So the other things would be examples, but let's go ahead and first look at this information. There is a test of continuity that you should familiarize yourself with. And so I have it copied from the text here. A function is considered continuous at a particular point if it satisfies the following conditions. First of all, the function defined at C, or whatever that X value is, has to exist. So there has to be a value there. For instance, we can say, just looking at this picture, this function is not continuous because it doesn't exist at, it's not continuous at 0 because it doesn't exist at 0. Same thing here. This function, if we zoom in a little bit closer, the second function does not actually exist at 0. This guy does not exist at -1. So already those fail that first necessity for continuity. All right, so the function is defined at C, in other words, that f of C exists. The function approaches the same y value on the left and the right sides of the function as x is equal to C, or as x approaches C. And then finally, the y value that the function approaches is the same as the y value that it is. And so that'll make a little bit more sense when we do some examples, but I wanted you to have the continuity test in your mind as we continue to think about these problems here. So it says determine whether each function is continuous at the given x value. So we have a couple things that we should set up. Okay, so in order to do this, I wanted to set up an opportunity for us to do the 3 things that we have to do for a continuity test. So the first thing is to prove that f of 1 exists, because we're trying to prove that this function is continuous at 1. So to prove that it exists, we plug 1 into the equation, and then we come up with the value. So f of 1, or the value of the function at 1, is 10. Hopefully you guys see that. Plug the 1 in. 1 squared is 1. 3 times 1 is 3. Plus 7 is 10. So we've got through the first part. The function actually exists at 1. Great. The next part is and they call it the function you should approach the same value on y of the y value as you approach x from the left and right. I call it sneaking up on the function because we're not really thinking about what's happening here. What we're thinking about is the values that the function seems to be approaching as we sneak up on it. This is weird. This has to do with a concept called the limit of a function. But for us, let's just sneak up on it. So what does that mean? We want to get super close to 1 from the left, but we don't actually want to be at 1. So I might start at, let's say, point 0.9, 0.95, let's say 0.99, and let's do 0.995, okay? And what I'm going to do is I'm literally going to plug it into this equation. Yes, use a calculator. I'm totally comfortable with that. And then I'm going to do the same thing from this side. So I might do 0.11, 0.105, 1.01, and let's do 1.001. And I'm going to plug these values into the equation. And yes, fine, use Desmos, use something that'll help you make this easier. Plug it in, and what we want to do is see that we are approaching the same number. I'm not concerned about this right now, but we want to seem to be approaching the same number on either side as we move closer and closer to 1. So what I want you guys to see is that I'm over here in Desmos. I put the function in as an f of x is equal to blah, blah, blah. And then so what I'm going to do is I'm going to just put in f of 0.9, and that's going to give me the values that I desire. So you don't have to calculate it or, keep plugging in different values, okay? So you can do this and get your values to plug into your chart, whatever values you chose. And so I'll continue having fun with this, and then I'll be back over to our work and I'll plug it in by hand. Okay, so you guys see that we have sloppily, but did it anyway. We put the information into our chart, and you can see pretty fairly that as we're moving in from the left and from the right, you can see that we are definitely approaching the number 10. And so now that we see that it looks like we're approaching 10, we confirm that agreement by saying, hey, the value of f of 1 was 10. when we were sneaking up on it from the left and right, it seemed like it was 10. Yes, there is agreement. What we thought we were approaching, we approached, and therefore we can say that this function is continuous at x equals 1. I know that was a whole lot. I guarantee you that that was a lot for me. And I know that you're looking at it like, clearly it's continuous. Can't we just graph it? This is a process in calculus that's going to help you develop a sense of the idea called the limit. And so that's why we want you to be able to play around with this concept a little bit right now. All right. So I'm glad you guys did it. We're going to do it again and maybe again so we can see. So we're going to do the same setup. We shouldn't take as long. We're going to do the same setup where we need to have our 3 circumstances, and then we're going to determine continuity. So in the first one, we've got continuity. Let's check these next ones. So in part B, when I check out the first thing, we got to prove that f of 2 exists if we want it to be continuous at this point. So that means I'm simply plugging it into the equation, 2 squared minus 4, and I get 0 over 0. I know I could factor out the x minus 2 and make this make sense a little bit more, but the fact is x does not exist at 2, and therefore this thing is not continuous. So we're going to go down to our next example. So as we're looking at this guy, first of all, does f of 1 exist? This is the third example. So if I plug 1 into this equation, well, let's look at it. It's a piecewise. It says this function exists here for 1, but it doesn't exist up here for 1. So what I'm saying is this is what we want to look at when we're trying to identify what f of 1 is, because 1 is within this part of the domain. So f of 1 will just be x. So f of 1 is 1. All right, that exists. We've done the first part. Let's sneak up on the point. Since we're looking at 1, we want to see what values happen as we come from the left and to the right. This one we're going to have to use, I guess we could use Desmos again. It's pretty easy to do it as we are coming up from the left side, because as we're coming up from the left side, x is just equal to itself. You guys see that? X is exactly what it is. So I'm going to just plug that in. So we've got 0.9, we've got 0.95. As we get closer, it seems like it's approaching the number that we expected. This might actually be continuous. Let's see. And so I don't really need to worry about this 1 value. We know that that's already 1. Now the next question is what's happening on this side as we are approaching. So 1 over 1.001 will be pretty close to 1, I'm sure. I think I'm going to employ some help from Desmos. Okay, so we're back over here at Desmos, and we've got f of x is equal to 1 over x, and I put in these values, and we can see, yeah, it's totally getting closer and closer to 1. And so I'm going to go report those values back into the other screen so that we can kind of make a comparison. All right, so this looks pretty good. It seems like everything that we need for continuity is here. We're approaching 1 in this direction. We're approaching 1 in this direction, and that agrees here. So we indeed do have agreement. And so by having that agreement, we also have continuity. All right, so in the interest of time, we're going to skip example 2, which dealt with continuity test again, so it wasn't too bad, and I think you guys will be fine without it. We're going to do example 3, describe the end behavior of this situation. So to describe end behavior, it's really helpful to have a mental picture of what the parent graph would be. So if you notice, both of these parent graphs would basically be y equals x cubed. Can you guys get that? Both of these polynomials would be kind of some kind of riffing off of y equals x cubed. And yes, I can plug it into a calculator and take a look at it and be like, I see the end behavior is this. But I want you guys to be able to have an idea of what the end behavior is without having to graph it. So how can we do that? Well, yes, we can put larger and larger numbers of x inside of the function and see what we get. I want you also to be able to think it through like this. If y equals x cubed is a function that does something like this, when I throw a negative coefficient in front of it, which we have in both f of x and case of g of x, when I throw a negative coefficient in front of it, we are going to get something that'll do the opposite. So it'll start up and it'll kind of do this. That's what's going to happen in this case. Notice the 2 is going to stretch it some, but it's still going to flip over the x-axis. And so this is what we have. And over here, this will have a very similar end shape, but inside the x squared minus x plus 5 is going to make it do a little dancing. So we might get something kind of like this. But again, this negative gives us this rotation over the x-axis where we start high and we end low with a cubic polynomial. And so with that, we have the information we need. So what is happening? So let's say this is for f of x. So as x approaches positive infinity and as x approaches negative infinity, that's what we're thinking about. What's going on? Well, as x approaches positive infinity, f of x is going down. So we have negative infinity. F of x is approaching negative infinity. And here, as x was approaching negative infinity, going that away, we see that f of x is approaching positive infinity. You guys see how we came up with that? And yes, you're right. It's going to be absolutely identical for the next situation. So I'm literally going to make a copy and just put it over here. And instead of having f of x, I'm going to change that to g of x because that's the function that we're now analyzing. That's going to have that same relationship. And you can take a moment if you like. You can check it out by graphing and kind of figuring out what it looks like. You can graph it, do a quick sketch of the graph, and get your answer in that way. This final example is going to require that we actually do some graphing if you don't know what the graph looks like. And it's actually best to do graphing at this point so you can kind of figure out how good your mental graphing skills are. So I know that this is a parabola. It's a negative parabola. Its vertex is going to be at positive 5, positive 3. So, and it's going to be kind of going down. That's what I'm assuming here when I graph it. This is going to be an absolute value function, and this where we have a v, where the vertex of the v is at negative 3 and negative 5. It's going to be kind of wide because it only goes up half as much as it goes out. And over here, we're going to have a cubic polynomial where we should generally have something that does one of these numbers like that because it's still going up in the positive direction. All right, so that feels good, but now I need some exact values because what they're asking us to determine are the intervals in which the function is increasing and the intervals on which the function is decreasing. Remember when we talked earlier about monotonicity? So this is the idea. We're thinking about the intervals, where exactly one thing is happening. So I'm going to go get some graphs. As promised, here are the graphs to each of these functions that we discussed. And now we're just going to talk about intervals of increasing and decreasing. So increasing, decreasing, and I'm just going to do that straight down the line. So we can see that this function is going to be increasing from negative infinity all the way up to 5, and then it's going to be decreasing from 5 down. So I'm going to just write it like that. Negative infinity up to 5, we are increasing, and then from 5 down, 5 up to positive infinity, we are decreasing. I hope I said that right. I think I wrote it right. All right, let's continue on with this. Similar situation here. You see how the graph really does help us get the interval correct. So from negative infinity on this function, let's see if we can get you to write, negative infinity all the way up to, what is that? Now, if I'm not mistaken, that is negative 3 as indicated by the shift over to the left. So all the way up to negative 3, we have a decreasing function actually. Let me grab that and move it over. So this thing is decreasing on this interval, but it's increasing from negative 3 on in the interval this way. Negative 3 on to positive infinity, increasing. All right. And finally here, let's do increasing, decreasing again. We've got a couple things going on. So from negative infinity to negative 2, we've got increasing, But then we have decreasing from -2 all the way up to +1. So I think that's +1, yeah. So from -2 to +1, we have decreasing, and I guess I can use a bracket here as well. And then we have it increasing again from +1 all the way out to positive infinity. And so there we have it. We talked a little bit about end behavior. We talked about monotonicity, increasing over particular values. We talked about continuity today. We talked about a lot of things. Hopefully it's making sense. Let me know if there's anything I can help you with in section 3.5 or before, and we'll talk soon. Take it easy.